So the easiest thing to say is, again, no 3A covered, but we'll finish chapter 3 today and then start it on chapter 4 and get through quite a lot of chapter 4. Real simple. All right. So last class period, I went over quite a few examples of finding zeros of polynomial functions. And we had that rational zeros theorem, right? And if you remember, rational zeros theorem doesn't mean there can't be other real numbers which are zeros. There can be other real numbers that are zeros, complex numbers that are zeros, but all the rational ones will look a certain way. Now, I bring that up because remember, a rational number is a number that's just written as a fraction. And what we're going to go into today in 3.7 is a rational function. So we've dealt with polynomial functions a lot in chapter 3. Now we're going to deal with rational functions. A rational function is a function that can be written let's use R for rational function. R of x equals P of x over Q of x, where the numerator function and the denominator function are polynomial functions. So it looks like polynomial divided by polynomial, all right? And we've dealt with a lot of polynomial functions in the first few. We know what rational numbers are, so we put those things together and we create a rational function. Okay, a rational number is integer over integer. Rational function is going to be polynomial function over polynomial function. Okay. So that's the basic idea. And if we're looking for properties of polynomial functions, well, or I say polynomial functions, properties of rational function. Well, let's take a look at some of the graphs of rational functions. There we go. So let's look at some graphs of rational functions. A lot of the rational functions that we'll deal with in this class, will have linear pieces on the top, linear pieces on the bottom. Sometimes we'll have quadratics on the top, quadratics on the bottom, something like that. But we won't get into huge polynomials, generally speaking. So let's take a rational function. Let's say x plus 7 over 2x minus 6. So we have polynomial x plus 7 divided by polynomial 2x plus 6. You'll notice that if you zoom out, there's this spot in which On one side, it moves up to infinity, and on the bottom side, the function moves down to negative infinity. All right? If you zoom in enough to where that is, that's actually at the number x equals 3, or the line x equals 3. That line is known as a vertical asymptote. All right? If you scroll out and you move over to the left as far as possible, what you'll see is that my function levels off as I move to the left. And as I move to the right, it also levels off. Okay? It turns out that just like this vertical asymptote, if you draw a line, in this case it's y equals 1/2 or y equals 0.5. It turns out that y equals 0.5 is also a line that this function approaches, but that's a horizontal asymptote. Okay. Now, I don't want you to think that all rational functions are going to have horizontal and vertical asymptotes. You could have a function that is a rational function that has a vertical asymptote. You could have one that has a vertical and no horizontal, or a horizontal and no vertical. There's lots of different options here. So let's take, for instance, x to the third minus x plus 4 and divide it by x minus 2x minus 1. Oh, x squared minus 2x, excuse me, x squared minus 2x minus 1. Oh, that's a weird one. So you'll notice that there's no horizontal line that when I scroll out, it gets closer to, right? As I move off to the right, this goes to infinity. As I move off to the left, goes to negative infinity. So this one does not have a horizontal asymptote. It does have a couple of vertical asymptotes, though. Think. All right. One of those vertical asymptotes is at, I believe, negative, no, not that one. Oh, you know what? I screwed that up. I should have put +1. Sorry. X equals 1. I'm sorry. This is the same type of thing. I just missed a plus minus thing. But you'll notice it does have a vertical asymptote. At x equals 1. All right, shoots off. But in this case, the vertical asymptote actually shoots off up in both directions. Shoots off to positive infinity on the right-hand side, and also shoots off to positive infinity on the left-hand side. Okay. That's what I was going for. So all kinds of things are going on there. We got vertical asymptotes, horizontal asymptotes. And we can kind of look at the behavior of the graph. as it comes in from one direction or another. Okay? So let me just write that down. Rational functions may have, again, may have vertical asymptotes. And horizontal asymptotes. And obviously they might not have either, or they might have both. All right, we saw one that didn't have a horizontal asymptote. There are ones that may not have a vertical asymptote either. Just so that we're all aware, asymptotes are lines the function approaches but does not touch. Now, here's the algebraic stuff that we're going to do. Okay? How do I find a vertical asymptote? One that's going up and down to positive infinity. How do I find a horizontal asymptote? One that's going left and right. Well, if you think about what's going on with a vertical asymptote or a horizontal asymptote, let's start with the horizontal asymptote. If my function is approaching a horizontal line, that means my function as it goes to infinity is getting closer to this line. So what a horizontal asymptote is, it is a behavior of a function as x goes to infinity, or on the left-hand side as x goes to negative infinity. So horizontal asymptotes are determined by the behavior of the function as x goes to either positive or negative infinity. And we're going to bring back that arrow notation we've talked about way back in 3.1. Okay, as x goes to positive or negative infinity. In a similar but we saw a vertical asymptote, so similar but different, obviously. A vertical asymptote means one side is shooting off towards infinity and the other's shooting off towards negative infinity, or they're both shooting off towards positive infinity, or they're both shooting off towards negative infinity. So what that means is vertical asymptotes happen when as x gets closer to a number, we'll just call that number A for right now. Then the function value goes to either positive or negative infinity. I use A just for asymptote value, if that makes sense. But so as x gets closer to a number, then the function shoots off to infinity. Function shoots off to negative infinity. Now let's think about what happens. How do we get a function shooting off to positive or negative infinity if we have a rational function? Let's examine this rational function. Let's make it a nice one. F of x is equal to 7 divided by x minus 4. Okay. And let me just sort of talk through how I look at this problem and what'll set you up for taking Calc 1. Because they do a lot of things with limits, and this is kind of what is dealing with limits right now. All right. So let me explain this. Let's pretend I have this fraction, 7 over a number. That number is x minus 4. If x gets really, 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 really big here, what's happening to this denominator? Well, it's getting really, really, really big, right? As x gets really, really, really big, the denominator goes to infinity as well of this function, right? What's 7 divided by really, really, really big numbers?
Really small.
Very, very small, right? 7 over a million, 7 over a billion, 7 over a trillion. That's a very, very, very small fraction. And as x gets bigger and bigger and bigger, I just put 7 over infinity. That's poor notation. I'm not saying that's good notation. So that means the entire function is getting closer to 0. Does that work? Is that okay? So the end behavior of this function as x goes to infinity is that my function goes to 0. That means I have a horizontal asymptote of, now be careful, it's not of 0. Technically, it's of y equals 0. So the equation of a horizontal line is y equals a number. All right. So f of x has horizontal asymptote of y equals 0. Okay. By the way, also, and I didn't write this down, but I probably should have before I wrote that horizontal asymptote. Also, if you think about it, as x goes to negative infinity, what's happening? 7 divided by negative infinity is a really, really small fraction in absolute value, but it's on the negative side. If you're really, really small on the negative side and really, really small on the positive side in absolute value, you're close to 0. So whether it's a positive or a negative fraction, in both cases, as x goes to infinity, my function goes to 0. As x goes to negative infinity, my function also goes to 0. So in this case, it goes to 0 for both. Goes to 0 for both. I probably should have put that before I said it's a horizontal asymptote, but that's not a big deal. So that's what we do for horizontal asymptotes. We just say what happens as x gets really, really big. Either it goes to positive infinity or goes to negative infinity. On the other side is the horizontal asymptotes. What's going to cause our function to go off to infinity or to go off to negative infinity? Well, if you think about this, 7 divided by a really, really, really small number small as in close to 0. So let me project this up real quick. I like bright projectors. I don't know why. Okay. So here's a calculator. If I do 7 divided by 0.1, that gets 70. 7 divided by 0.01 is even bigger. 7 divided by lots of zeros. And then 1 is huge. That's 7 times 10 to the 11th power. Okay. Oops. You see that? There's a little bit of a my bad. On my screen, it looked all right. So what's happening? As your denominator gets really, really, really small, the fraction goes off to infinity. And by really, really small, I mean an absolute value. If this were a negative number in my denominator, it's still, well, in this case, it's going to negative infinity, right? All right. So as this fraction has a denominator that's getting closer and closer to 0. Then 7 over something that's close to 0 is going off to either positive or negative infinity, depending on which side, whether we're dividing by negative numbers or dividing by positive numbers. Does that make sense? So my point is, as the denominator gets really, really big and the numerator stays the same, the entire fraction went to 0. As the denominator goes to 0 and the numerator stays the same, the entire fraction goes to infinity. So there's kind of an inverse relationship there, right? Between 0 and the denominator and the fraction going to infinity and infinity in the denominator and the fraction going to 0, right? Now in this case, when is the denominator 0? Well, in this case, the denominator is 0 when x is at 4. And because my function shoots off to infinity there, I'm going to have a vertical asymptote of the line x equals 4. By the way, you'll notice that 4 is also not in the domain of my function, because if I plugged in 4, I'd be dividing by 0. So most of these rational functions have domain all real numbers except when we're dividing by 0. We can't divide by 0. Is that okay? Now, just because we have a good example here, and we kind of know what's going on, I've tried to explain it. I want to introduce some new arrow notation. This is specialized arrow notation. So the specialized arrow notation is X arrow A, and then we either put the plus sign or the minus sign in the exponent. Right? This one means X is getting closer to A from above, meaning larger values of A. And this means the exact opposite. Means X is getting closer to A from below, meaning the values are slightly smaller than A. Now, here's why we need that special notation. Let's once again examine my function I was just dealing with, 7 over x minus 4. All right. If I say what happens as x goes to 4, well, it turns out from one direction, 4 is going off to negative infinity, and from the other direction, we're going towards positive infinity. Does that make sense? Because the vertical asymptote has one side going up, one side going down. So as x goes to 4, that's kind of going in 2 different directions. You okay with that? So what we do is we say, well, what happens as x goes to 4 with slightly larger values? Well, what's going to happen if this denominator is really, really small? But if my values are slightly above 4, this denominator is always going to be positive. Right, get that? This is like dividing by 0.1, 0.01, 0.00001. So as x goes to 4 from above, then my function is going to go towards positive infinity. And the exact opposite happens if x goes to 4 from below. If my numbers are slightly smaller than 4, the denominator is going to be negative. It's going to be negative 0.1, negative 0.01, negative 0.0001. And so when you divide by negative numbers that are really, really small, your function goes to negative infinity. Are you okay with that? It's not too terrible. So let's go back to Desmos. So 7 over x minus 4. So that, there we go. notice that as my function gets closer and closer to 4, from x values that are above 4, it's shooting off to positive infinity with x values that are above 4. With x values that are below 4, it's shooting off to negative infinity. That's what we mean by that arrow notation with the plus minus. Plus just means a little bit above that number, minus means a little bit below that number. Okay. Any questions about that? All right. Good. So that's the special arrow notation. Special arrow notation with the plus minus. You don't need that for infinity because you can only go to infinity in one direction, right? And the same thing for negative infinity, you can only go in one direction. But for every other number, you can either come in from higher values towards it, or you can come in from lower values towards it. All right, so there you go. So let's take a look at another. Let's find the arrow notation. And find the asymptotes, both vertical and horizontal if they exist, for the following function. Let's say we'll call it g of x equals 6x minus 1 divided by x plus 5. It's a little bit different. Let's do this one together. All right, a little bit different. So where do you think let's start with the vertical asymptote. That's actually a little bit easier. Where's the vertical asymptote gonna be?
-5.
At x equals -5, right? Vertical asymptote. Happens when the denominator is 0. By the way, on this function, it happens when the denominator is 0. I will make a little asterisk on that. There is one exception to when the denominator is 0, and the only one exception is if there is a common factor on top and bottom that needs to be eliminated. Okay, so if we've reduced our fraction, then vertical asymptotes happen when denominators are 0. So when we've reduced our fraction, I'm just gonna write that down. When we reduced fraction, have a reduced fraction. I don't give you non-reduced fractions. I don't try to trick people, all right? But if you're moving along and you say, hey, in math 124, I learned that denominator 0 means asymptote. yes in the reduced fraction version, okay, of whatever rational function we have. So this one doesn't have any common factors that you can factor and cancel out. That's my point there. All right, so vertical asymptote happens when the denominator is 0, and that means when x is -5. So vertical asymptote of x equals -5. Good. Now let's use the arrow notation around -5. And in particular, as x goes to -5, and the numbers are bigger than -5, what's going to happen? As x goes to -5 and numbers are smaller than -5, what's going to happen to my function? Which side shoots off to infinity? Which side shoots off to -infinity? And why? I'll give you a hint. One of them shoots off to positive infinity, one of them shoots off to negative infinity. Or does it? Think about when x is going to -5 from above. From above, that means numbers that are a little bit above -5. All right. What's the bottom of my fraction going to be? It's going to be small in absolute value, but is it going to be positive small or negative small? If x is a little bit above -5. Let's say -4.8.
It would be going to negative infinity, right?
The whole fraction or the denominator?
The denominator.
So if x is getting closer to -5 from above, do something like -4.8. -4.8 plus 5 is a positive 0.2. That makes sense? So my denominator is going to be positive small if x is going to -5 from above. What's my numerator going to be when x gets close to -5? Well, my numerator is going to be 6 times x minus 1. As x gets close to -5, that's going to be basically -31. Right? About -31. Just like we had 7 from our previous example, it's going to behave just like -31 does. And if I have -31 divided by a positive number that's really, really, really small, like -31 divided by 0.1, -31 divided by 0.001, -31 divided by 0.00001. It's getting towards -infinity. Does that make sense?
Mhm.
As x goes to -5 from below, my total fraction, well, in the denominator, it's a negative, really small number, really close to 0. And my numerator is still about -31. Sometimes I don't even put about there, I just put -31 over. And if it's negative over negative, then it's gonna be positive. And obviously shooting off to infinity because the denominator is getting really, really close to 0 again. So the arrow notations look like that. Around the asymptote, x equals -5. Does that make sense? Let's do the other way. Let's look for horizontal asymptotes. Horizontal asymptotes, we're going to look at the behavior of the function as, oh shoot, I misspoke. Of my function as x goes to positive or negative infinity. I miswrote that. Look at the behavior of the function as x goes to positive or negative infinity, right? So let's take a look at this. As x gets really, really, really big, what's going to happen? Well, both the numerator is going to get really, really big, but also the denominator is going to get really, really, really big. Okay. That didn't work, did it? It'll work in just a second. Here's the trick. As x gets really, really, really big, this -1 here and this +5 aren't going to matter very much. If x is 1,000,000 and then you add 5 to that, you don't change the total size of the fraction. Denominator. 1,000,000 denominator versus 1,000,005 denominator, that's not that big of a difference. If you go 1 billion, doing 1 billion, dividing by 1 billion versus dividing by 1 billion plus 5, not going to change a whole lot, right? Same thing with the numerator. Having a numerator of 6 times 1,000,000, so 6 million, subtracting 1 doesn't change it very much. 6 billion minus 1, that's not that much different than 6 billion. So what I'm saying is, as the x values get bigger, the largest growth on top and the largest growth on bottom are going to sort of take over, right? So I can just look at the highest, the leading term on top versus the leading term on bottom in the context of leading terms that we talked about a couple of sections ago. All right, meaning the term with highest degree. And what's that do? 6x over x. Well, That's just 6. So as x goes to infinity, then g of x goes to 6. Leading terms dominate. Now that's the same way in the other direction too. So as x goes to negative infinity, then g of x also goes to 6. Leading terms dominate. So what are we saying? Well, we're saying we have a horizontal asymptote of y equals 6. All right. Let's confirm that by graphing. Oops, thought I was sharing. Not sharing the screen yet. So we have g of x which is equal to 6x minus 1 divided by x plus 5. Oops. Sure enough, if you look at what's happening, as your x gets closer and closer and closer to -5, on the right-hand side, a little bit above -5, we're going off to negative infinity. As x gets closer and closer to -5 from the left-hand side, we're going off to positive infinity. We do have x equals -5 as a vertical asymptote. Let me change the color on that. And as you go out to positive or negative infinity, look at how that line flattens out. And we're getting closer and closer and closer to a y value of 6. When I get really, really big x values. So you can see both my horizontal and vertical asymptotes there. That makes sense? So that's how we find asymptotes in a rational function. To find the horizontal asymptotes, what we're going to do is we're going to let x go to infinity and know that when x goes to infinity and x goes to negative infinity, then the behavior of the graph is going to be dominated by the leading term of the polynomial on top versus the leading term of the polynomial on bottom. Okay. When we're looking for vertical asymptotes, we're basically looking for where the denominator is 0, so long as we don't share any like common factors on top and bottom, which you're not gonna be given any common factor ones in my class. All right. And that's basically the whole thing. There is one other thing I should mention, and that is, where do we have X and Y intercepts? We can also find those if we want in the very exact same way we've done before. So let me go through this example. But this is just a continuation. I don't have the room to write on the board, so I'm just gonna keep here. Does that make sense? Whatever. So let's also find the X and Y intercepts. Of G of X, the same G of X. How do I find the X intercept? How do I find the Y intercept? Well, how did I do that in every other type of function, right? Every time you find a Y-intercept, you plug in 0 for X. Every time you find an X-intercept, you plug in 0 for Y. So let's find the Y-intercept first. Y-intercept. Plug in 0 for X. -1/5 is what I get, which is -0.2. There. So the Y-intercept, the place where it crosses the Y-axis is 0, -0.2. Pretty close to the origin, but not the origin. To find the X-intercept, plug in 0 for Y. Y value is just your output value. So we get the fraction 6x minus 1 is equal, divided by x plus 5 is equal to 0. How am I going to solve that? And multiply both sides by x plus 5, yeah. Multiply both sides by x plus 5, and what happens here is it clears out the denominator. X plus 5 times 0 is just 0. So if you multiply x plus 5 times both sides, that just means the numerator is 0. And hopefully we know that about fractions. For a fraction to be equal to 0, the numerator has to be 0, right? So all we're doing is essentially setting the numerator equal to 0 and then solving. That's why I didn't show the x plus 5 multiplication. So some people would say multiply both sides by x plus 5. Other ones would say, well, if a fraction is 0, the numerator has to be 0. Either way, fine. Add 1, then divide by 6. So x is 1/6. Which is 0.16666 repeating. All right, I won't go into that. I'll just say the x-intercept is 1/6, comma 0. So there we go. So we found the vertical asymptote, we found horizontal asymptotes, we found all of the arrow notation, we found now x and y intercepts, and that's basically all that we need to know about rational functions, other than being able to recognize them. Once now we have all of these things, now we should be able to recognize the graph of a rational function too. You can also recognize the graph of a rational function by simply graphing it on your calculator, right? Or on Desmos, typing it in and saying, oh yeah, it looks like that. So other than recognizing the graph of the rational function, this is basically what we have for 3-7. So let me ask you to do another one on your own. Let's do all of the things we just did for this function. Let's take another function. Let's find the asymptotes, both horizontal and vertical if they exist. X and Y intercepts. And the arrow notation around the asymptotes. I'll write that down, but arrow notation around the asymptotes for another function. Let's take f of x equals 4x plus 28 divided by x minus 3. This one is reduced. There's no common factors, so don't worry about that weird asterisk. Try doing this on your own. Vertical asymptotes, horizontal asymptotes. All right, so let me go through this, okay? I'm going to look for my vertical asymptote first. I say vertical asymptotes, singular, because I know there's one place where the denominator is 0, but if the denominator happened to be a quadratic, there might be 2 places where the denominator could be 0, right? You could have 2 solutions. If the denominator was cubic, there might be 3 places where that cubic could be 0. And all of the stuff that we did in those previous sections, if the denominator is a polynomial of degree n, then we might have n zeros, right? Places where the denominator could be 0. And then we might have that many vertical asymptotes. I've made the problems in this section, a lot of them are linear over linear. But if your polynomials are of higher degree, then you just turn back to what we did in earlier sections. Does that make sense to solve for 0? So vertical asymptotes happens when f of x is simplified and the denominator is 0. So we have one vertical asymptote and it's x equals 3. Again, if the denominator is quadratic, you can solve a quadratic and you might get 2 asymptotes. You might get none because certain quadratics can't be solved over the real numbers, right? And you might get complex solutions, which means you don't have one. But in this case, we got one vertical asymptote. That's when the denominator is 0, when x equals 3. Now, as x gets closer and closer to 3 from above, and x gets closer and closer to 3 from below. I want you to notice, I'll write it on the same line, that f of x, if x is a little bit more than 3, is my denominator positive and close to 0 or negative and close to 0 if my x is a little bit above 3? Well, if x is a little bit above 3, and I subtract 3, like 3.01, 3.0001, I'm going to get a positive number that's close to 0. So I'm going to say positive close to 0. I'm going to put positive small last time. So I'm just trying to give you multiple options of ways to think about it. But it's positive, but it's close to 0. What's going to happen if my numerator is close to 3? Well, I'm just going to get 4 times 3 plus 28, whatever that happens to be. What's 4 plus 3? To be 4 times 3 plus 28? That's about 40. So there you go. $40 over a positive close to 0, that's positive over positive, gives me infinity. Does that make sense? As x goes to 3 from below, I get 40 divided by a negative number, which is really close to 0. So I get essentially that my function is going towards negative infinity. As x is below 3. Is that right? Making sense where I'm getting that from? When in doubt, if you ever doubt yourself, use your calculator to graph it and just confirm that that's what is going on, right? There's no special pat yourself on the back because you didn't check your answer, right? I'm so good I didn't check my answer. You can always check your answer by just graphing it and looking to see, oh yeah, from the right-hand side above, we're going shooting up towards infinity. And numbers below 3, we're shooting down towards negative infinity. So just graph it and check it if you're ever in doubt. Now, as far as the horizontal asymptotes, I'm going to shorten what I did from my last example. The way I'm going to shorten it is to say, as x goes to either positive or negative infinity. So I'm going to treat these kind of the same at the same time. So as the x value gets really, really, really big or really, really, really small, then my function behaves like 4x over x is equal to 4. I just look at the leading terms and I compare those. So that means my function goes to 4. And that means I have a horizontal asymptote of y equals 4. I'll come back to that in a minute. To find my y-intercept, plug in x is equal to 0. But it's 28 over 3, some ugly fraction. We'll just call it 28 over negative 3. All right. Negative 28 thirds. So y-intercept is the point 0, negative 28 over 3. Doesn't reduce, sad. All right, let's go x-intercept. Plug in 0 for y. Fraction can only be 0 if its numerator is 0. So set the numerator equal to 0. And then solve. X is -7. So the x-intercept is -7, 0. That work?
That's what I got.
That's what we got. Good. Everybody get that? Good. Now, I do want to mention before we go, I have been working basically exclusively on linear over linear functions. Okay, so far. That's what we've dealt with. All of these same principles hold true if my polynomial function on top is degree 5 and my polynomial function on bottom is degree 7, right? It just is more complex. To find vertical asymptotes, you have to get rid of any common factors and then set the denominator equal to 0. And then if you have a 7th degree polynomial on the bottom, solving that 7th degree polynomial equals 0, you have to use some hard stuff to do that with. Okay. If we're looking for the horizontal asymptotes, the function still behaves like leading term over leading term. They're not always going to cancel out. For instance, if it was 5th degree on top and 7th degree on bottom, let's say, for instance, you ended up with leading term of 4x to the 5th over x to the 7th. How would that reduce? Well, that would reduce like 4 over x squared, right? And as x gets bigger and bigger and bigger, what's this do? It goes to 0. Does that make sense? So your horizontal asymptote would be y equals 0 as x gets bigger and bigger and bigger. If it were reversed, if it was 4x to the 7th over x to the 5th, then you have 4 times x squared. And as x gets bigger and bigger and bigger, what's this do? Well, it gets bigger and bigger and bigger, right? So that goes off to infinity, which means you don't have any horizontal asymptotes. Everybody okay with that? So it's still leading term comparison. It's just, if the terms don't match up, you say, oh, if the bigger thing's in the denominator, it's going to 0. If the bigger thing's in the numerator, go into infinity. So there's no horizontal asymptotes in this case. To find the y-intercepts, still just plug in x equals 0. Find the x-intercepts, plug in y equals 0. And sometimes that's harder to solve, sometimes that's easier to solve. So again. So all of the same principles hold when you have higher degree polynomials, but most of the time, for sake of making problems that are doable in a fairly short amount of time, most of the time I have linear over linear. Okay. In all of the homework problems, it's linear over linear, and the test problems will be linear over linear. All right. Any questions about that? Mitch? Well, then I'm gonna move on to 3.9. 3.9 is all about variation. And you'll see multiple different phrases for variation that mean the same thing. We're gonna look at 3 different types of variations and then combinations of those. Really, it's just 2 different types and combinations of those. All right. So variation just means there's a relationship, and it's either going to be a multiplicative or a division relationship. So these 2 phrases, and there's probably others that are similar. Y varies directly with X, or Y is directly proportional to X. Both mean that there's some equation Y equals K times X, where K is just a real number. That K is also called the constant of variation. It's the constant of variation. So those 2 phrases both mean Y equals KX. Right? That's direct variation. Inverse variation or Y is inversely proportional both of those phrases, Y varies inversely with X or Y is inversely proportional to X, both mean we have an equation which is Y equals K over X. Again, K is some real number called the constant of variation, again here. There's another phrase that the book uses a lot. You know what I should have done? Sorry, let me use a different letter, excuse me. So I'm gonna do this one. W varies jointly with X and Y. Or W is jointly proportional. To X and Y. Both of those phrases, jointly proportional or varies jointly, both mean W is equal to my constant of variation and then times X and also times Y. The jointly just means both multiply. It's kind of like directly and then directly again. I'll write K as a constant of variation. Again, it is, but. And so we can use this idea of variation to come up with, one, lots of different equations that relate two variables together. And then two, to solve problems using the idea of variation. Okay, so there's lots and lots of combinations of between these three ideas. Does that make sense? Let me give you an example. Things we might say. So let's start right with writing an equation for the following statement. Z varies directly with the square root of t. So z varies directly with the square root of t. Varies directly means we're going to take our constant of variation, which again, we just always use k unless it says use otherwise. And we're going to multiply it times what we're varying directly with. Now, previously, all of my phrases, it's just been a single letter. What if it says varies directly with the square root of t instead of just t? Well, I'm just going to use square root of t rather than t. So z equals k times square root of t. So that's like step one. Can we write stuff like that? Then we can say if z is 56 when t is 49, then what is z when t is 25? I'll do my work while we're here. So the first thing I need to do, if I'm saying when t is 25, I could plug in 25 into here, but I don't know my k yet, right? In order to find the k, I have to use this information. So I use this first sentence, or first part of the sentence, to find k. So I say z equals k square root of t when t is 49. T is 56. So I just plug those in. I find my value of k using the standard square root of 49 is 7. Divide both sides by 7, you get k is equal to 8. All right. So that's step one. Now I know what this k has to be. Since k is 8, now we can answer what is z when t is 25. Becomes a really easy thing to do, right? I know that k is 8. I'll do it this way. When t is 25, what's z? 8 times square root of 25? I think that's 40, right? So there you go. Any questions about that? Is it pretty easy? As long as we know the proportionality, direct means multiply, indirect means divide, joint means both are multiplying. We can do all kinds of combinations of different algebraic versions. Let's do another. Other similar thing, but we use different letters and different variations and different proportionalities. Write an equation for y is inversely proportional to the cube of x. That's not cube root, that's just cube. That's x to the third. Is that okay? So write the equation for that, and then say if y is equal to 80 when x is equal to 3, then what does y equal? When x is equal to 4. Yeah, that's good. I want you to try this one on your own. We're gonna get y equals k over x cubed. First equation. Maybe a couple more minutes to finish it up. All right, so let's go through this. It says y is inversely proportional to the cube of x. So if y equals 80 when x is equal to 3, what does y equals when x equals 4? First off, I always want to write the equation with an arbitrary constant variation. Okay, in this case, that's y equals k over x cubed. And then to solve this problem, we'll use that first line. Y is equal to 80 when x is equal to 3. Well, I just need to multiply both sides by 3 to the third power. And if I multiply both sides by 3 to the third power, I get a k of 2160. Is that right? So just multiply by 3 to the third on both sides. Or 27. Okay, that's what 3 to the third is. So since K is 2,160, what do you say, Y, when X is 4? So I go back to my equation. I said I know K is 2160. I know X is 4. So I put that in. And as a decimal, I got 33.75. I don't know what that is as a fraction, probably an ugly fraction, but yeah, 135/4 is a fraction. And that's basically all of the proportionality. Now, by the way, just so that we're all on the same page, you could have just as easily said when y is equal to 80, x is equal to 3, what does x equal when y is some crazy value, right? So you could have also given the value of y and then solved for x instead of giving the value of x and solve for y. Does that make sense? So you could have known this one and then solve for x just as easily. So that's the idea of proportionality. Obviously, we can do jointly proportional if we want. Then you just have to have you have to know what x and y are, and when w is this number. You can do all kinds of w is jointly proportional with the square root of y and the square of x. So you have square root of y and then x squared, right, in there. You could have all kinds of different combinations. You could say w is directly proportional to y, but indirectly proportional to x at the same time. And so your y would be multiplied and your x would be divided. All kinds of crazy combinations. But what I would like to do is I would like to check out at least a couple of word problems on this inverse proportionality and direct proportionality and joint proportionality. And to do that, I'm going to look at some problems from our book. I don't normally do this, but when we deal with word problems, it's kind of nice to not have to write a lot on the board, or at least not have to come up with new things, new ideas. So this is section 3.9 of the book. And I'm in the problems section. There's lots and lots of problems if you want to try these. So you can see all of this. Like number 32 says y varies inversely with the square root of x. When x is 64, then y is 12. Find y when x is 36, you know. Y varies jointly with x and y when x is equal to 4, z equals 2. Oh, x and z, excuse me. Y varies jointly with x and z when x is 4 and z is 2, then y is 16. Find y when x is 3. And it's the same type of stuff we were just doing, right? So most of the first few are exactly what I just did. Okay. So let's go to some word problems. It says the distance, which they're calling s. I don't know why they call it s distance. Seems like we call it d distance, but they use s. Who knows why? So the distance that an object falls varies directly with the square of the time. So s varies directly with the square of t. If an object falls (16 feet in 1 second), how long will it take to fall 144 feet? Everybody okay with that? Notice that when you set it up, it's almost identical to the stuff we were just doing. S is the distance fall, varies directly with the square of t. So S is equal to K times t squared. Now it says object falls 16 feet in 1 second. That means the S is 16 when the T is 1. Remember, T was in time, and S, for some reason, represented the distance fall, that the object fell. Excuse me. Well, 1 squared is just 1. 1K is just K. So K is 16. All right. By the way, this is the constant of variation. You know what this is also called? This instance is the constant of gravity. I'm talking about how long something fell in a second. So that's the constant of gravity, constant variation. And what we're saying is the constant of gravity is 16 feet per second squared. That's not important to this. It's not important to things, but that's what it is. 16 feet per second squared. All right. So we know that S is equal to K times T squared. And how long to fall 144 feet? Let me write that down. How long fall 144 feet? Gotta answer that. S is equal to K times T squared. K we said is 16. Now that 144, is that the S or the T? S, in this case. In this case, 144 is the S. And so I need to solve this one for T. This is a pretty straightforward solving a quadratic. 144 divided by 16 is 9. Now, if we were actually solving the quadratic, T could either have been the positive square root of 9, or T could have been the negative square root of 9. In this instance, having a negative time doesn't make any sense. So we can cross that one out, right? So algebraically, T could have been 3 or negative 3, but practically, we're asking for a time it takes. And it's not gonna take negative 3 seconds to fall 144 feet. It takes 3 seconds. So it takes 3 seconds. Fall 144 feet. Any questions about that? That's pretty easy or not too bad? Crazy. Good. Then let's look at another one. Let's look at number 53. Rate of vibration of a string under constant tension varies inversely. So I'm looking at 53. Constant string under constant tension varies inversely with the length of the string. If a string is 24 inches long and vibrates at a rate of 128 times per second, what is the length of a string that vibrates at 64 times per second? All right, notice that they didn't give us any variables on 53. So we're gonna have to make up our own. So rate of vibration, what letter do we want to use for that? It doesn't matter, I'm just asking you, do you have a preference on letters?
V.
V, all right. Rate of vibration, we'll call that V, vibration rate. Of a string under constant tension varies inversely with the length of the string. Anybody care about length of the string, letters? Doesn't matter to me. I'll use an L, and I'll use a capital L because sometimes a lowercase L looks like a number 1 when I write it on the board. But so maybe I should use S for string. It doesn't matter. If you want to use S for string, that's fine. If a string is 24 inches long, string 24 long. And vibrates at 128 times per second. All right. What is length of string that vibrates at 64 times per second? All right. I want you to try this on your own. Try this example. On your own. Wait, 6.4 times. Oh, no, I wrote that. This should be 64 times per second. I'm sorry. I think something's wrong. 24 twice. 64. I wrote it on the board incorrectly. All right, so let's take a look at this one. Well, V varies inversely as L. V is how many vibrations, L is the length of the string. So V equals K over L is our inverse proportional equation without the K filled in. In this particular, under this particular tension, a string of 24 inches would vibrate at 128 times per second. If I multiply both sides by 24, I forgot the number now, I get 3072 is equal to K. So 3072 after I multiply both sides by 24. What's the length of the string that vibrates at 64 times per second? Well, the vibration rate I know is equal to K over L. In this case, 64 is the vibration rate. The K is 3072. And so I just need to solve that equation for L. And multiplying L on both sides would give me 64L equals 3072. We don't get that multiplied by L on both sides. And then divide both sides by 64. So you need a length of string is to be 48 inches. So if you want to vibrate this thing slower, you need a longer string. What it's saying. By the way, this kind of motivates something. The idea of proportionality is very, very common idea. As you increase by a certain factor, the output is increased by a similar factor, right? Or in this one, if I I double the length of the string, the vibrations get halved, right? That's kind of a weird concept of this. And I don't even need to really know that as I double the length of the string, the vibrations are gonna get halved. Because if you just double the length of the string, that's like putting a 2L down there. Well, what's that gonna do to my vibrations? It's gonna divide by 2. Does that make sense? If I double the length, that length gets doubled. The vibration gets halved. And that's something about variation that's common. Let's talk about direct Y directly proportional. Proportional. To x. Okay. So y is directly proportional to x. Means y is equal to kx. Let's talk about a change in x. Compared to the effective change in y. If, let's say the change in x is to double x, what happens to y? Well, if x gets doubled, it becomes 2x, and just y is going to get doubled as well, right? Y is also going to double. If x gets multiplied by a factor of 5, and I'm just picking out 5, so we're timesing x by 5. Everybody follow that? We're increasing by a factor of 5 means multiplying by 5. What happens correspondingly to y? Well, if you multiply that by a factor of 5, then the whole thing got bigger by a factor of 5. So y also got changed by a factor of 5. And those are both increases. But if you do a factor of, let's say, a third, that's going to decrease the size of x by multiplying, hopefully this is not x2, this is times 2. Does everybody understand that? Times 5 times 1/3. So if you multiply by a third, what's the corresponding change in y going to be? It'd be a third, right? Direct variation has this feature. That is, if y is directly proportional to x, no matter what the change in x is, there's going to be an equal corresponding factor change in y. Okay. Now let's do y is inversely proportional to x. First, right? Y equals k over x. If x is doubled, the denominator is doubled, and so the change in y is that y gets cut in half. If the change in x is to be tripled, what's the corresponding change in y? X is triple,
1/3.
1/3, exactly. And in the reverse, if the change in X is, let's say, 1/4, so it gets cut by a factor of 1/4, what's gonna happen to Y? Well, it's gonna quadruple times 4. This is where the names come from, right? Directly proportional means if you change a value for X, you directly change by the exact same value for Y. All right? Inversely, we're talking about a change in X produces the reciprocal change in Y. Now, this is just for like Y inversely proportional to X and Y directly proportional to X. Direct means same, inversely means reciprocal change. But we do have to be a little bit careful, and I'll just do one of these. Let's say Y is directly proportional to the square of X. If the change in X is doubled, then the change in Y is a times 4, right? Because 2 squared is 4. So that's quadruple. And if the change in X is tripled, so times 3, then we have to go 3 times 3 as the change in Y, which is a times 9. As we got to go square. So when I say that's where the words come from that with Y directly proportional to X, Y inversely proportional to X. But if you throw in something like X squared, then obviously it changes it in the appropriate manner. And if you threw in a square root of X, then doubling would be a factor of square root of 2. And tripling would be a factor of square root of 3. Change in the corresponding variable. That makes sense? So again, that's where the corresponding change comes from. Now, this is all of section 3.7 and 3.9. This obviously is, we finished 3.7 earlier, but 3.9, this is the end of 3.9. This is all we're doing in 3.9. Next class period, we'll come in, we'll start chapter 4, which is exponential functions. Okay? All right. Well, that's all I have for today. So I will see you all next time.